so super grateful to my co-organizers, but especially Alex Slivkins, who like really led this thing and made it. Take care, Mike. Special. That last 2 years were also a year on plus for Alex. So thank you.
Yeah.
Great. Yeah.
It's Krishna Darasartha talking about learning networks. Thank you.
And also say thank you so much to all the organizers and to the center staff. Great. So Kevin started with a paper of ours that secretly didn't have a network, and now I'll tell you about a paper of ours that does actually have a network. And so this is about how networks matter for Bayesian social learning. And so, right, let me start with a sort of broad description of the type of social learning setting that we've seen earlier in this conference. We have a lot of agents. They're learning about some unknown state. They're all going to have some private information about the state, and they're also going to observe some neighbors' actions. And so we're going to be particularly interested in settings where you don't necessarily observe everyone else who might be acting, or sort of everyone possible. And the main question that we're going to ask is, how does the structure of the social network or the observation network affect how efficiently information is aggregated? So I think with this audience, I can jump into some of what's known about this. There's a lot of theoretical work on Bayesian social learning on the complete network, so settings where in some sense you see all the other agents or everyone who you could possibly see. There's some nice work on Bayesian social learning on networks that says eventually in many settings, agents learn the state on all networks that are reasonable in some sense. And I think some of you know these results. I'll tell you what this means formally if you don't later on. But the takeaway from this is that there's less known about how Bayesian social learning compares across networks. And if we want to ask the question, the main things that we're going to have to ask about is not sort of long run learning, but in some sense, how well signals are aggregated or how quickly rational agents learn. And so we saw a version of this in Omer and Kate's paper yesterday. This is going to be a quite different model, but similar sort of question. Did somebody? No. Great. And so just as a little backup for this being something that people are interested in, here's a quote from a survey by Ben and Evan that says, a significant gap in our knowledge concerns short-run dynamics and rates of learning. And what these models mean here is Bayesian models of social learning and networks. And so let me tell you what we do about this. We introduced what we think is a tractable model of rational social learning that lets us compare learning across different networks. And in particular, we'll get a measure that will let us rank many networks with respect to their efficiency for social learning. The main sort of obstruction to learning that we're going to be looking at is what I'll call network-based informational confounds. And so let me give you a simple example of this. It could be that I see Alex and Nicole take actions. They both observe Rachel taking an action, but I don't see Rachel. In this case, from my perspective, Rachel's action is going to confound the behavior that I see Alex and Nicole taking. And so even if I'm rational and I can account for this, I may not do as well as if I saw what Rachel had chosen to do. And so these types of intransitivities are going to appear in many networks. And we're going to see, it turns out it's not too bad in this case, but in some other examples, these intransitivities can lead to arbitrarily inefficient social learning. And one class of networks that we think demonstrate this nicely are what we'll call generations networks, where agents arrive in successive cohorts, and each cohort observes the cohort before them or some of the cohort before them. In these generations networks, under some symmetry condition, we'll be able to express the rate of learning as a simple function of some network parameters that I'll tell you about. And one of the implications of that formula is going to be that almost all of the information is lost. So under the symmetry condition, learning is going to aggregate no more than 2 signals worth of information per generation asymptotically. I'll tell you what that means formally soon. But the takeaway here is that these generations may be large. They could have 100 or 1,000 people each. Each of these people is getting their own private signal. But the learning from one generation to the next is going to lose almost all of those signals. It's only going to get you, in the best case, a bit under 2 signals worth of information. Okay, great. So I don't want to spend too much time on the literature, but let me just say there's a class of nice papers that find in various ways network structure doesn't matter too much for sort of outcomes like long run learning. There's also a lot of interest in comparing networks and different types of social learning models. But this usually, most of the existing results are either, say, comparing 2 networks or doing numerical simulations in settings where it's hard to get analytic results. And so we'll tell you about a framework where we can get some analytic rankings of broader classes of networks. There's also some nice papers, I guess, one of which we saw yesterday on other obstructions to the efficient learning rate, like course actions, where my action doesn't fully reveal my belief, or endogenous information acquisition. We'll ask some similar questions to these literatures, but we'll ask it in a setting where we abstract away from these other obstructions, and the obstructions are really just coming from network structure, and that's what determines whether you learn better or worse. Okay, so let me tell you the model. It's all on this slide. There's 2 equally likely states. Omega is either 0 or 1. It's a sequential model, so agents arrive one at a time. They're each going to observe a private signal. I'll tell you how that works soon. They'll observe the actions of some neighbors, and then they'll choose to act. And then after they take their action, they're done. They're gone from the model, and somebody else arrives. These neighborhoods are going to determine the network structure. So the neighbors are the set of people before me who I see, and so we can think of this as defining an observation structure. If we know who each person sees, that's going to together give us a network. What are they going to do with this information? They're going to pick an action that's a real number between 0 and 1. And they're going to want to minimize the square distance from the state. And so it's standard that this implies that their action is just going to be equal to the probability that the state is 1 given their information.
Can I just make sure I understand the first bullet point?
Yeah.
So there's a network, but then the agents move in order. Is that network dependent, the order in which they move? Or is it just you're just going to any order of agents? So I'm kind of confused between the moving in order and the network.
Yeah, so what's the right way? So you can think we fix an order of agents, and then we define a network on these agents in this order with the condition that you can only observe people who came before you. So this is equivalent, I guess, to the network being a directed acyclic graph, given that the order doesn't really matter. You could think of having some set of agents with a network before the order, and then if you wanted to translate that into this, you could say, I observed the people who I have links to who moved before me.
Okay.
And so we're not going to think about how you go back and forth between those 2 networks, but that's something you can do, and there's some other work on.
Okay, thanks.
Great. And so what's really going to be important for everything other than sort of the welfare where we need an actual utility function is that the action space is rich enough to reveal beliefs. So the action I choose reveals my beliefs about the state. The maybe most substantive assumption we make is that signals are Gaussian and conditionally IID given the state. What does that mean in this binary state setting? If the state is 1, the signals are going to be Gaussian with a mean of 1 and some variance. If the state is -1, they're going to be 0, they're going to be Gaussian with a mean of -1 and the same variance. So what's this going to imply? If I see a positive signal, the state is more likely to be positive to be 1 than 0. The more positive it is, the more likely it is to be 1. And conversely, a negative signal implies the state's more likely to be 0. The lower the signal, the stronger the belief. The neighborhoods are, so the network structure is common knowledge, and agents are Bayesian and choose optimal actions given observations in predecessors place. So you can think this is Nash equilibrium, but there's nothing strategic. And so you don't really need that. Since this is the whole model, happy to take questions, but I'll just give you a minute more to see it, and I'll comment on, I think a lot of this everything here is assumptions that sometimes appear in this literature. The two that are not the most common are these continuous actions and the Gaussian signals. And what we're going to see is that the combination of these two assumptions leads to some nice properties that let us say things about the model. Yeah.
There's no notion of payoff anywhere.
This is the payoff, sorry. The expectation is, or yeah, the payoff is distance, negative distance from the state space. Okay, great. So let me get into what's nice about this model and then tell you about a couple of examples. So the first nice property, which some of you might expect given the Gaussian structure, is that we're going to get linear actions in some sense. And so to see this, we're going to need to work in the space of log likelihoods. And so I can turn each signal into a corresponding log likelihood that of the state being 1, and turn each action into a log likelihood of the state being 1 that would rationalize that action. These are bijective changes. And so we can think of the actions or strategies as being mappings from your log signal and your neighbor's log actions to your log action. And so the first result says this map is linear. This is coming from the Gaussian information structure. And so formally, my log action is equal to my log signal plus some weighted combination of my neighbor's log actions. And these weights are going to depend on the network structure. The proof gives an explicit formula for them. I won't tell you that now, but what you can think is if two neighbors' actions are more correlated, I might downweight them. If somebody's action is more accurate, then I might upweight it and put more weight on it. And there's a formula that tells us how to do this. I'll maybe also mention, this is coming from the Gaussian signal structure. It's maybe not for exactly the same reason as usual. And so it turns out to be because of this nice fact that with a binary state and this Gaussian signal structure I told you about, the log likelihoods are also distributed as conditionally Gaussian random variables. And so given that, you can get this. And so it's from Gaussian, but for sort of not exactly the same reason as in most Gaussian economic models.
This updating is almost like a two-group model.
Sure. It's almost like a two-group model. I guess there's no way to think about whether the weights are time invariant, right? For certainly across people, they're not time invariant, but yes. Yes, you will elect that the weights are endogenous. Yeah, okay, so this is something that might not surprise you too much. Another feature of this model that did surprise us more is that we can interpret the accuracy of an agent's action in terms of an equivalent number of independent private signals that you'd have to get to take the same action. So what do I mean by that? Well, first of all, if somebody just got n independent private signals, it turns out that their action would take this form. It would be normal with this distribution. Don't worry too much about the details of this. These constants are coming from this transformation from the signals to the log likelihoods, which were also Gaussian, but with some other distribution. But what I want you to think is this is, if I see n independent signals, my action is Gaussian with some fairly simple distribution. I'm going to say social learning aggregates R signals by agent I if their log action has this distribution for some real number R. And so what I'm doing is I'm taking the distributions that you get if you see n independent signals for any n, and I'm interpolating between the integer values of n. Something to highlight about this is if agents take arbitrary actions, even if their actions are log linear, and so we still have all this normal structure, this condition doesn't have to hold. It's imposing a particular restriction on how the mean and the variance of their action distribution relate. In general, they could be taking actions that would lead to sort of all sorts of normal distributions with all sorts of mean and variances. And so they don't, and the actions that they could take, even if they were doing something nice and linear, don't have to have this form. The reason this is useful is the rational log actions always satisfy this definition. They always admit this type of signal counting interpretation. And so formally what this is saying is that there's some integers Ri such that social learning aggregates Ri signals by agent I. It turns out these depend on the network, but not on the signal structure. And so the reason this is useful, well, there's a couple of reasons, but the main reason this is useful is that these RIs give a sufficient statistic for the accuracy of a rational agent's action. So in general, their actions are going to, if we didn't have this, their action would be some distributions. It's sort of a pain to compare one agent's action distribution to another. With this, if we want to ask, say, is one agent learning better on one network than another, we can just compare these sufficient statistics. We can ask, is the RI smaller for that agent on one network than the other? Another way of saying this is it's saying we can measure each agent's accuracy in units of independent private signals.
These are signals that I'm not understanding.
Yep.
When you say, it seems a little funny to me that should be exactly, I mean, I guess what's surprising is that you said something about interpolating, but I missed it. Why is the first argument necessarily an integer? Why will it's not, or?
These don't have to, R can be any
Oh,
number.
I'm sorry, I was okay.
So the point, what I was saying there is,
Got it.
if you have an actual integer number, you can't, it doesn't make sense to have 1.5 private signals, but we're just going to interpolate to define 1.5 private signals worth of information.
And when you say states, what does that mean? Like in,
Yeah. So right. So everything is conditional on the state. So what this is saying is it has this distribution with a plus here if the state is 1 and a minus here if the state is -1.
and last question, when you like the variance being exactly what it is, I mean, a priori it could have been that it wouldn't look anything, it wouldn't look like that for, you couldn't, mean and variance wouldn't be related in that way. So I guess you're saying that it's a result that it is.
It's a result. It's a bit magical to us. So I don't have like, we have to,
I see.
we prove it, but I don't have it.
So the signal counting interpretation isn't like trivial.
No, we don't think it's trivial. It's, it's, you can, any like more generic, if you choose some generic degree-dish rule, then it's going to tell us. Okay, great. So let me give some examples that are going to show you how the signal counting interpretation works and also what these confounds in our model that I promised you looked like. And so let me start with the simple example that I told you verbally in the introduction with 4 agents. Agent 1 gets a signal that says the state's more likely to be 1. They take an action that corresponds to that. 2 and 3 arrive. They don't see anyone, so they also get their signals and take the right actions given that. And then 4 arrives, sees 2 and 3, and has to figure out what to do with their signal and these 2 signals they observe. And in this setting, because everything is, the whole setup of the model, including the network structure, is common knowledge, agent 4 can back out 2 and 3's private signals from their actions. And so agent 4's action is going to be equivalent to if they knew 3 independent private signals. In fact, they do know 3 independent private signals. And so they can optimally combine 2, 3, and 4 signals because they can calculate all of them. Yeah.
You go back. Maybe you should finish the example before. I'll ask my question after you finish the example.
Okay, great. So what happens now if 2 and 3 observe 1? Now 4 has this problem where 4 sees 2 and 3, but doesn't see agent 1's signal or action that's influencing both of their actions. And it turns out that they can't fully incorporate 2 and 3 signals without overcounting 1s. They face this inevitable trade-off between overweighting 1 signal and underweighting 2 and 3 signals. They're Bayesian, so they're going to deal with this trade-off as well as they can. It turns out the optimal signal extraction underweights 2 and 3 signals somewhat, overweights 1 signal somewhat, and ends up with an R4 of 3 2/3. So they're doing as well as if they had 3 2/3 independent signals worth of information. This is in fact better than if they had no access to agent 1 signal. It's not too bad, but there is some information loss here. They're losing 1/3 of a signal. I'll take this question and then I'll show you that this can get much worse.
Could you go to the previous slide?
Yeah.
Your mean and variance for the normal distribution are the same dimension. Usually the mean and the standard deviation have the same dimension.
Yeah.
There's variance on it, after the comma is variance, right?
After the comma
is variance, right, for the normal distribution.
Well, so if I see n independent signals, then the variance is going to scale linearly in n, right, by this independence.
Right. So should the mean be 2 over sigma or sigma squared?
It should be sigma squared. I'm not going to be able to recreate this calculation on the board, but I'm pretty sure that these constants are both coming from this change from the signals to the log likelihoods, and it turns out that they come in sort of the same dimension from that. But yeah, this is right. I'm like fairly sure, but I don't remember the details of the algebra.
So should I be thinking of R as some kind of signal to noise ratio?
Opinion on this, Kevin.
It's in some sense saying how informative is this person's action, right? That's a piece of information about.
So yeah, in the sense, I don't think in the sense that right, it's a measure of informativeness, which you can think of as being about signal to noise. I don't know if it's signal to noise in any sense. I'd be happy to talk about it more, but I don't know if it's signal to noise in any sort of more formal sense than that. Okay, so
Are you gonna, keep going? There we are, stop. Okay. So can you go over again this bit about the trade-off that P4, the agent 4 has? You were saying that they have a trade-off between underweighting.
maybe I can write. So they're going to observe two actions, which are going to be they're going to know these two things. This is the wrong notation. What do I call? Is it lambda?
They know the actions, right?
What?
Go ahead, keep going.
Kevin, what do I call that? Okay, great. That was our old notation. That's no longer here. Okay, so they're going to see the sum of the log likelihoods corresponding to these two signals, which they can back out from this section, and the sum of the log likelihoods corresponding to these two signals, which correspond to 3's action. And so they're going to choose some weights. It turns out by symmetry they're the same, but they're going to fill out on their signal plus some weights on these two things that they see. And so what's going on here is they would like to put the same weight on lambda 1 and lambda 2 and lambda 3, but there's no weights you can choose that'll do that. Whatever they do,
I see, okay.
puts.
All right, thanks, that's very helpful.
So yeah, I guess in fact they'd want to put weight 1 on each of these 4, but there's no way to do that. Great, so I told you this can be much worse. Let's stick with the sort of same setup but add more agents. And so now we're going to have 3 generations of different sizes. This top generation of agents doesn't see anyone, so they just report their signals. The second generation sees everyone in the first generation, and then there's one final agent who sees the second generation. And what we get here, what we can calculate, it turns out really all you need from this is that you can get this from that signal counting interpretation, is that the change in accuracy between generations 2 and 3 is equivalent to getting this many private signals, this quantity here, and whatever k and k prime is, however big these generations are, the change in accuracy between the second generation and the third is less than 3 additional signals. So these RIs are going up by less than 3. There's little change in accuracy. There's very little learning between generations 2 and 3. And it turns out that this is true even if k is small. And so this bound, this 3 bound would hold, for example, even if there was only one person in the first generation.
But not if there's 0.
Not if there's 0, right? So if you had 1,000 people in the second generation, if there were no one in the first generation, then that's great. They just all tell you their signals and you get 1,001 signals worth of information. But if they all just saw one person and took the optimal action given that one person, then you would do much worse. I think you would get less than 5 signals worth of information. And so almost all the information would disappear.
So it seems like this is different from what was going on in Omar's talk yesterday. It's not that these people are incorporating the private signals, they're just looking at old information. It's that they just can't back out the information.
Yeah, I think that's it. So yes, and in particular, this is very dependent. They had a bound that was independent of network structure and would hold for any strongly connected network. I guess these aren't strongly connected because they can't be in our setting, but this is very dependent on the network structure. So if you put one link, if you had one person here, if you put one link from this person to the first person, then everything is okay. And so this is saying some networks lead to much worse learning than others. And certain types of network structures can generate this confounding. I don't have tons of time, but maybe I can tell you, I could give you some examples. This is a lot of the intuition for one of the main forces, but maybe I can tell you something about what happens on sort of non-finite networks. So the first question we can ask if we want to go beyond finite networks is, when do we get long-run learning? And so I'll say society learns completely in the long run if actions converge to the true state in probability. And this turns out to be equivalent to these RIs, the equivalent number of independent signals converging to infinity. And so the result here is going to be society learns completely in the long run if and only if the index of an agent's most recent neighbor converges to infinity. This is equivalent to a condition that some of you have seen. It's called expanding observations in this paper by Asimoglu and co-authors. So I don't want to spend too much time on this because many of you may know it, but it's mild and clearly necessary. If this fails, then there's some finite set of agents such that infinitely many agents only observe agents from that finite set. That means you can't learn, because if you have infinitely many agents with only finite access to finitely many signals, there's no way to learn. What this is saying is that this clearly necessary condition, this sort of necessary obstruction to long-run learning, is the only one. So as long as this sort of natural obstruction doesn't hold, you do get long-run learning. This is harder to prove in the model in this paper I cite, but it turns out to be fairly straightforward in this model because our actions are continuous. But so the takeaway from this is that we get long-run learning in almost all reasonable networks, and so it's not a very useful criterion for asking questions about which networks are good for learning. Instead, a criterion that we find is useful in many examples is what I'll call aggregative efficiency, which is the limit of Ri over I. And so what this is what fraction of the signals in the entire society do individuals aggregate under social learning? So if I'm the 100th individual, Ri over I is, I'm taking an action equivalent to as good as if I knew Ri private independent signals. So Ri over I is, I'm doing as well as if I knew what fraction of the signals that have arrived so far. And we're going to ask, what does this look like in the long run? What fraction of all the signals in the long run are getting sort of incorporated into social learning in this sense? Yeah.
Why didn't you guys divide by the number of neighbors you see? So divided by the total number of signals.
Because you can have, yeah, so the direct neighbors is sort of not enough because you can learn indirectly from other people. If I see somebody and they see someone else, I can learn from them. Something you could do instead that sort of is divide by the number of people who there's an indirect path from me to. It turns out these things are going to be the same in the examples I look at, but if you think there's sort of a lot of physical constraints where I don't see a lot of people in the network, then you might want to sort of do something more subtle that accounts for how many people I can reach, but this is just a simple measure that works nicely in many settings. And so something to point out here is we can have long run learning, this Ri going to infinity, but Ri over I near zero or even equal to zero in the limit. So we can be getting there very slowly, learning quite efficiently, even when we're on this big class of networks where we're eventually. In the paper, I won't go through this now because this is a shorter talk. We show that higher aggregative efficiency implies higher, well, networks that have higher aggregative efficiencies give higher welfare if the welfare function is sufficiently patient and if signals are not too precise. So if signals are very precise, you might have sort of all the welfare happening in the first, everything that matters for welfare, more or less happening in the first few agents, and you might need to look at what's really going on in the finite network. If signals are not too precise, you can look at this measure to ask which networks lead to higher welfare. Yeah.
Is the fact that agents are only acting once the reason why you can say something about welfare? Trying to think, sort of compare between this paper and Homer's yesterday. Why there were welfare implications there?
I think it's really coming. Yeah, I was trying to think about, we were talking to Moritz about this yesterday. I think what's important for it is that the bounds that we give, these RIs are independent of the signal precision. And so we had this problem in the paper yesterday where essentially if you changed any of the parameters, you might change the sort of time until the results kick in that Omer was talking about in response to some of the questions. And the fact that we have this independence of the information structure means there's a parameter that we can change that sort of makes the limit matter without changing the time until our results kick in. And so I think that's the difference there. I really don't have too much time, but let me spend whatever it is, 5 to 10 minutes comparing networks for social learning by comparing their aggregating efficiency. And so I promised you these generations networks. I'll at least have some time to tell you about what we call maximal generations networks, which are networks where agents arrive in successive cohorts and observe everyone in the previous cohort. So everyone in each generation T, each generation has size K. You can think these are like different classes of the university or cohorts at a firm. Everyone in generation T observes everyone in the previous generation. And so here's an example with 3 agents per generation. 4 and 5 and 6, all see 1, 2, 3, 7, 8, 9, see 4, 5, 6, and so on.
I just want to tell you that you have 11 to 12 minutes left.
Amazing. Okay. Well, maybe you'll get to hear about a little more of this. So in these maximal generations networks, we can give a fairly complete description of learning outcomes. The first thing, here's an expression for the aggregative efficiency. It turns out to be 2k minus 1 over k squared. What does this tell us? Well, one thing that it tells us is in the long run, social learning aggregates fewer than 2 signals per generation with any k. So this is this point I made at the beginning. Even if the generations are large, we're only getting 1.5 or 1 3/4 or 1.9 signals worth of information, even if there's 1,000 or 10,000 signals arriving in each generation. You can ask how things depend on the generation size. So yeah, let me put both of these. There's fewer signals aggregated per agent with larger k, but more signals aggregated per generation with larger k. What does this mean? Well, if you want to ask, are larger generations better? You can ask a couple of questions. You might ask, if I'm the 100th person, would I rather have larger or smaller generations? The answer there is smaller because the larger generations generate this confounding. You can also ask, if I'm in the 100th generation, do I want larger or smaller generations? The answer there is larger is a bit better because it's just more signals that have arrived that I can access. But what this is saying is that I lose almost all of that information. So there's not very much benefit. Even if I know I'm in the 100th generation, having bigger generations before me only helps a little.
Both, you weren't comparing across different, both people were in the 100th generation. Or did I, was that right?
Yeah. So I did 2 things. The first was you're the 100th person. How big do you want all the generations to be?
Oh, I got it.
for that one, you want the generations to be small, and intuition is if all the generations are size 1, then you can see there's no information loss, there's no confounds. The other one, sorry, this was fast, was if you're in the 100th generation, you want bigger generations because it's just more signals that arrive by the time you show up, but it doesn't have to be very much. We can also get a shorter rundown, which says that after generation 2, social learning aggregates fewer than 3 signals per generation with anything. So these 2 signals per generation is a long rundown here. It's saying after the first 2 generations, we can get a bound that's only slightly worse. And this sort of comes from the example that I showed you. So yeah, let me tell you a little bit more about how we can think about these bounds. The first thing that we can see is social learning has to aggregate at least 1 signal per generation. That's because I can always take my private signal, choose some action I see, and optimally combine them, and I'll do 1 signal better. What the lower bound is saying, what the upper bound is saying is that this lower bound is not too far from the actual learning. We might do better than 1 signal per generation, but in the long run, no better than 2, and even in the short run, after the first 2 generations, no better than 3. And again, if the generations are large, this is saying we're aggregating only an unboundedly small fraction of the private signals. Let me tell you a little more information from this. Some of this might have shown up earlier, but it's this, the basic force behind this is the same trade-off between overweighting generation T's private signals and underweighting the common social information that came before. And the idea behind this result is that when the generations are large, the optimal action severely underweights the private signals from generation T. And so in this example here, you're underweighting a bit. As these generations get large, you're underweighting very severely. And so I guess we won't see this later, but it turns out from the proof that the total weight on private signals from a generation T approaches 1 as T goes large. This is much less than you would like. You would like to be putting weight 1 on each of the private signals, but instead you're putting a total weight 1 on all of them. Okay, I told you this verbally. How long do I have? A few minutes. Okay, so yeah, let me tell you in the last couple of minutes a little bit about how other types of networks compare. And so,
question just to get
yeah,
intuition. So if you threw in some naive agents here that or broke some links so that they didn't see anything, and we're only acting on their own signals. I'm trying to think of how much that would help, or the problem is you'd have to have very specific patterns of them over time in order to help.
yeah, good. So yeah, we had some discussion of this in some version of the paper, and so roughly, if you have some people who say only observe their immediate predecessor, maybe this when I talk about other networks, but you could have some people who say observe. You could have lines of people who observe sort of the person in the same position in the previous generation, but no one else. They're not going to be subject to any confounding, and so you can make one person or some of the people do better by sort of sacrificing some of the other people. And so depending on sort of what your welfare function is, whether people in certain positions matter more than others.
You could leverage them heavily, right? So you could have lots of people observe them.
You could have lots of people. And so if you have a lot of people where you don't care if they're learning badly, then you can have the other people do much better. But there's what we think is basically a conjecture is that the only way that asymmetry can help get around this bound is by sort of totally sacrificing some people to help others. And you can sort of do calculations if you want on the optimal version of that. I don't have very long, but so yeah, let me just a question that we go on to ask in the paper is, what if you have other types of network structures? So we're going to keep this generation structure, but we're going to say, what if you don't see everyone in the previous generation? And so here's an example. On the left is this maximal generations network we've seen. On the right is a network where everyone sees 2 neighbors, but not the third person in the previous generation. So the first person sees the first two, the second person sees the second and the third sees the first and third. And so you might wonder which of these are better for social learning. And I think it's not obvious because the left-hand network gives more observations. People just have more information. On the other hand, it has a lot more overlap. And so there's more of this confounding. And so to answer this, we need an expression for aggregative efficiency on more general networks. I think I'm running out of time, so I won't really tell you how that works. But what I will tell you is we can get an expression under a symmetry condition for the aggregative efficiency in settings where agents have the same degree and have the same number of common neighbors. A couple of takeaways from this. First of all, it turns out that this aggregative efficiency is less than 2 over k. This term in parentheses is less than 2. And so this generalizes our bound of aggregating at most 2 signals per generation to any of these sort of symmetric networks. Again, it wouldn't hold if you did what Matt suggested, but if you had this symmetry, you aren't going to do better than this. And you can also make comparisons about how the aggregative efficiency depends on these different parameters. So let me go back to this. That was all a bit fast, but it turns out plugging into this formula, these two networks give the exact same aggregative efficiency. The extra social observation on the left exactly cancels out the reduced information content from the overlap in this. So let me wrap up all, since this has been a long day. We told you about what we think is a model of rational sequential learning that's helpful for analytically calculating how social networks affect how well information is aggregated. In general, the network structure can lead to confounding. And in certain types of networks, including many of these generations networks we looked at, this confounding can be quite severe, and you can end up losing most or almost all of the information. Thank you so much.
So I guess following up on Matt's last question, it seems like you could try to sprinkle sacrificial lambs around to help, but one could maybe summarize your point you're finding by saying that indirect social, insofar as social learning is genuinely indirect, that part is very slow. If you sprinkle in some direct learning opportunities, you can speed things up. But the confounding, it seems confounding applies when indirect observations somehow. When I'm trying to aggregate information from people I don't directly see.
Yeah, so what I was trying to say, I don't know if what I was trying to say to Matt is a structure that does well for some people is if you have a bunch of these things where there's no confounding, and then maybe this person over here sees all these people. And so you can get some, you can sort of have some sacrificial lens can still allow some indirect learning because you really need these sort of intransitivities, but this seems, yeah, we sort of think this is probably the best you can do.
Yes, I wonder, like, it seems the efficiency arises because people are just smart, they try. Yes. And like, if there were things, like if they assume,
yeah,
then it would be.
No, this is even worse. So we have another paper on a version where they think everyone's actions are just their independent private signals. And there you don't even necessarily get long run learning. You get convergence to wrong beliefs with positive probabilities. One thing that does help is if people put more weight on their private signals, if they sort of, which you might think, you know, it's a naive thing to do, but it's socially beneficial. If I put more weight than is privately optimal on my private signal, that's going to sort of decorrelate my action from other people's actions and help the people who observe me. And so we have some results about that. And I guess that's something that's sort of observed in behavioral economics as a real effect.
Thanks, everybody.
Okay, thank you.